All right, everybody, hello and welcome back. Today what we are going to do is we are going to work on analyzing the graph of polynomial functions. All right, so as you can see, I've got my polynomial f of x at the top here, the graph we're going to use to sketch, and then I have all of these different things that we're going to take a look at in terms of this polynomial. Okay, so these are all questions we are going to answer, and almost all of them are things that we've already seen before, except for really this section right there. Okay, so we'll kind of get to that a little bit later. For now, let's start with the things we are familiar with. Okay, so I've got my function over here. F of x is equal to 3x to the third power plus a 6x squared minus 3x minus 6. Well, the first thing we want to do is take a look at our end behavior, and hopefully we are familiar with end behavior, and we know that we want to look at the degree, which is 3, right? That is our highest exponent here. And then our leading coefficient, which is also 3. So those two things tell us some important information. So our degree is 3 and 3 is odd. That tells us our end behavior is going to be opposite. So as x goes to the right, our function f of x is going to do what? And then as x goes to the left, our function is going to do what? All right, so these two things are going to be opposites. And because our leading coefficient is 3 and 3 is also positive, that tells us that we are going to go down to the left and then up to the right. So this is what I was talking about. These two things are going to be opposite because our degree is 3. So all that really means is we're going to be going up in this direction and down in this direction. Now, we don't know a whole lot about what's going to be happening in between just yet, but we are going to get there. The next thing we want to do is we want to find our zeros or our solutions so it can help us find our x-intercepts. All right, so if you notice, we have 4 terms here, so that means I can try to factor by grouping. So I'm going to group my first 2 terms and my second 2 terms. If I take a look here and try to find the greatest common factor of each of those first 2 terms, I realize that a 3 and an x squared goes into both parts. Now if I divide my 3x cubed by a 3x squared, I am left with just x. If I divide my 6x squared by a 3x squared, I am left with 2. And then I'm going to do the exact same thing with my other grouping here, but I've got a negative 3x and a negative 6. So both have a negative 3 that can multiply into it. And again, I am left with an x plus 2. So I know I'm about to finish with the right answer because my values inside these 2 sets of parentheses are the same. So I'm going to have one grouping of 3x squared minus 3. And then my other grouping is going to be an x plus 2. Now, one thing that I need to be aware of is this part right here. And it's really our first step in factoring should have been to divide out our greatest common factor of all of our terms, which is 3. But I could see that still come into play down here. So I'm going to divide out what those 2 terms have in common. And I am left with an x squared minus 1. And I still have that x plus 2. Well, hopefully we recognize that this is going to be a difference of squares pattern, so I can break this up again. And I'm left with 3 times x plus 1 times x minus 1, right? That splits into those 2 parts. And I still have that x plus 2. Now, my solutions, my zeros, are going to be what I would get if I set each of those values equal to 0. So my zeros are going to be, well, if I set this equal to 0, I get x equals negative 1. I get x equals positive 1. And I get x equals negative 2. So those are my solutions. I've got a negative 2, negative 1, and positive 1. Our fundamental theorem of algebra tells us I've got an exponent of 3, so I should have 3 solutions, which I do, which is great. All right, so those zeros are important because they actually help us find our x-intercepts. Our x-intercepts are going to be negative 2, 0, negative 1, 0, and positive 1, 0. That is why we wanted to find those zeros or solutions in the first place. Now, the next thing I need to do is find my y-intercept. The y-intercept, if we think about what it is where we cross through our y-axis. Well, the x value is 0 on our y-axis, so I could just take my original equation here, and I could plug in 0 for each of my x's. Now, if I do that, this will go to 0, this will go to 0, and so will this. The only thing I am left with is that -6. So it should be pretty easy to find our y-intercept when we're in standard form like this. But just to kind of show us the work that goes into it, I plug in 0 for each of my x's. So I'm going to have a 3 times 0 to the third plus 6 times 0 squared minus 3 times 0 minus 6. So f of 0 gives me a -6. So my y-intercept is 0, -6. All right, so I've got that plotted here. 1, 2, 3, 4, 5, 6. And now I'm getting a little bit more accurate with my graph. So the next thing we need to consider is how high in between these points we are going to go and how low. So it could look something like this, but it could also look something like this. Or it could look something like this, maybe, if I went through my y-intercept. We don't really know, so we need to find what we call our extrema values. The extrema values are our local maximum and minimum, our absolute maximum and minimum. All right, and so we can't really find those without using calculus. So what we are going to do is we are going to take a look at the graph. All right, I've already have this graphed over here for us. As you can see, we got that function at the top, 3x to the third plus 6x squared minus 3x minus 6. So I've got some key points here. All right, I've got about -1.55 and 1.89. So -1.55 and then let's see what we said there. 1.89 on my left side, and then on my right side, I'm going to go to 0.21 and then -6.34. All right, so I like to go to 2 decimal places just to be consistent. Again, I would ask your own teacher to see what their preference would be. So that's important for us because it tells us that at -1.55, or like roughly right in the middle there, we're going to go up to almost 2, so right about there. All right, and then we're going to go down in this direction and actually pass through and get to right about there. So at 0.21, so just past our y-axis, we're going to go to our lowest point, which is a little bit past -6. So let's just say right about there. And then I'll label these for us as well. So these are what we call our extrema values. Now, what I can do is I can, and I will do this in black here, is I can connect our points, hit each of those high and low points, and then we should have a pretty accurate graph of what our function is going to look like. So this is where those extrema values come into play. We've got locals and absolutes. Well, we can pretty much tell what an absolute is. It is the absolute maximum value or absolute minimum value, depending on what we're talking about. As you can see from our end behavior, we've got arrows in both directions. So what that means is we're going to continue to go all the way up on the right side and continue to go all the way down on the left. What that means is we are not actually going to have any absolute maximums or minimums. Now, we will have local maximums and minimums. And local just means compared to the points around it. So is there a maximum point compared to the points around it? And is there a minimum point compared to the points around it. These are those values. All right, so if we take a look at the left point over here, the one we first plotted, it is higher than the points directly around it. So we say it is a local maximum. Now, the local maximum value is a value of our function, which is 1.89 when x is negative 1.55. All we're doing is we're saying, hey, our function has a local maximum value at 1.89 when the x value is negative 1.55. Again, we're just giving some more important specific information about our function so we can create a little bit more of an accurate representation on our graph here. Now, our local minimum is the same idea. It is a point that should be lower than the points immediately surrounding it, and that is this one. So the minimum value is negative 6.34 when x is 0.21. And again, there is no absolute minimum here. So those are extrema values, locals and absolutes. Locals are comparative, so compared to the values right next to it, and absolute are total. So an absolute maximum is the absolute highest the function's going to go. Well, you don't have those because of these arrows. These arrows just point and tell us our function is going to continue to go all the way up. Now, we do have to talk about our increasing and decreasing, and these are really supposed to be intervals. So what I like to do is I like to try to highlight where our function is going to be going up and where it's going to be going down. Well, on this entire section here, we should be increasing until we hit that local maximum value. So the interval should be all x values from the left all the way until 1.55. So from the left, from negative infinity all the way until negative 1.55, we are increasing. So that is our first interval of increasing. Now, we also have an interval on the right side, and it is past this local minimum value. We are increasing again, and we read functions from left to right like sentences. So I'm kind of just tracking across and seeing, oh, I'm going up and then down. So this would be an interval of decreasing in the middle and then up again. So I'm increasing starting from that local minimum. Well, the minimum value is our x value, 0.21, and we're increasing all the way to the right. It never stops increasing. So we're going to move further and further to the right side all the way until positive infinity. Now, since we've got two intervals, we need to say, hey, both of these situations, both of these intervals are intervals where we are increasing. So we need to use our union symbol, which just means both of these. This one and this one, I guess is a better way to put it. Now, our decreasing is going to be the only missing interval. If we think about we're going all the way from the left to the right, well, we are missing this chunk here, which is between our extrema values. All right, so it is between the x values of negative 1.55 and 0.21. It is the values that are in between these two parts. And if you think about it, what happens is we have everything accounted for. We've got this section, which is increasing, this section, which is decreasing, and then this one, which is increasing. It is our entire domain of values. Now, since our function has arrows in both directions, our domain is going to be from negative infinity to infinity. And then our range is going to be the same because there's nothing that stops us from going up and down, negative infinity to infinity. So the domain should be directly linked to our intervals of increasing and decreasing. And now this is the representation of our graph and a pretty good analysis of it. Now, one thing I did want to talk about is what we call turning points. And turning points are the number of extrema values that we are going to have. So for example, we have 2 here. Well, we really can figure out how many extrema values we should have from our degree. Our degree here is 3, which is odd. So our possible turning points are going to be even numbers less than 3. So that is going to be 2 or technically 0. So potentially this function could have 2 turning points like this, which include this turn and this turn. Now, turn is where we go from increasing to decreasing, or decreasing to increasing. So it's those 2 parts there. Or we could have 0 turning points, and it could be kind of smooth like that. So an example of what that might mean is if we've got a function with a degree of 7, let's say, then technically we could have 5 turns. Oh, we should go even numbers. We could have 6 turns, 4 turns, 2 turns, or 0 turns. Now, we won't really know, but it gives us an idea of what we should be looking at, what our different possibilities are going to be. So that's going to be an important idea for us from here on out, something that we always need to consider when we start to set up our graphs here. All right, so let's take a look at another example. And here we've got g of x is equal to -2 times x plus 2 times x minus 1. Now, this is in what we call factored form, so it's a little bit of different information for us. But we can see that we have one x value here and another one here. So that means our degree is going to be 2. Each one of them has a multiplicity of 1, so we only see 2 values here. And our leading coefficient is what we can see all the way in the front, which is a -2. And the reason I know that is because inside here it's just 1 and 1. So if we were to multiply this whole thing out, whatever we would have, our leading term would just be our a value here. So we can pretty much find our end behavior here, but let's take a look at our number of possible turns. Now, because our degree is 2, that means we could have an odd number of turns less than 2. Well, the only odd number less than 2 is 1. So that tells us this function is only going to have one extrema value. It's only going to have one of these. All right. Well, this is a quadratic, right? We've got a degree of 2, and we know what quadratics look like. It's either going to be concave up or concave down. All right, so we should know that it's going to have one turn, but let's jump right in and do some of our end behavior here. So our end behavior is as x goes to the right, our function, and this one is g of x, is going to be doing what? And as x goes to the left, our function is going to be doing what? Well, if our degree is 2, 2 is even, that means our end behavior should be the same direction, either both up or both down. Now, because that leading coefficient is negative, that means we're going to be concave down, so both ends need to go towards -infinity. So we're going to go down in this direction and down in this one. So we're just piecing it together at the moment. So just like before, we're going to look at our factors here to find our zeros. And the zeros are important because the zeros tell us our x-intercepts. So here are zeros of -2 and 1. And again, we've got 2 of them, which is great because our fundamental theorem of algebra tells us because our degree is 2, we should have 2, and we do. So that means my x-intercepts are at -2, 0, and then +1, 0, and now we can start putting together our other pieces. A y-intercept. Well, this isn't in standard form, so it's not quite like this last one where we could just look at that value all the way at the end. So what I would need to do is I need to try to plug in 0 for x, just like we did on the side here. All right, because it's really what a y-intercept is. It's where a function is when the x value is 0. So I'm going to go ahead and take my function and find g of 0. That means in place of each of my x's, I'm going to plug in a 0. So this will leave me with -2 times 2 times 1, or a -4. So my y-intercept is 0, -4. Oh, this should be a -1. There it is. I'm always good for one mistake here. So that means we have a +4. So our y-intercept should be at +4. And we now know that our function is going to look something like this. Well, I need to find my extrema values. And again, I should only have one. So what I'm going to do is I'm going to jump over and take a look at the graph. Again, because we would need calculus to do this otherwise. Here we can see the shape we had in mind was correct. We've got our y-intercept, our two x-intercepts, and then we've got that point right there, which is -1/2, 4.5. Let's do this. So I've got -1/2, which is right about in the middle, 4.5, which is right about there. And now I can go ahead and connect. And that's what our function is going to look like. And again, it's pretty accurate because we know what that extrema value is. Well, now we need to think about, is it a local or an absolute? Well, local is compared to the values around it. So if we look at it, we see, hey, that is the highest point of the points around it. So technically it is a local maximum. Now, it is also an absolute maximum. The reason it is an absolute, because that is absolutely our highest point. There's no higher point around it. So I'm going to go ahead and label it as both. All right, and your teacher might have a slightly different preference. Technically, absolute maximums and minimums are locals as well. So you could list it as both, and that's what I'm going to do. So my absolute maximum value is that 4.5 when x is -0.5. And again, I'm going to do that for both. So the local maximum value is 4.5 when x is -0.5. So I've got that kind of written down for both, again, because technically compared to the points around it, it is a high point, so it is local, but it's also the absolute highest point, so it is the absolute maximum. Now, when we talk about minimums, we've got arrows pointing down, which means they're never going to stop going down, and therefore we are not going to have any minimum values. Now let's do increasing and decreasing again. So we read a graph like we read a sentence. You start on the left side and you start moving to the right. As you can see, we are going up here. So we're going up from our arrow, which moves all the way to the left and all the way down. But our increasing and decreasing should be x values. It is intervals. So we are increasing from all the way to the left, right? Because this arrow is going to keep going down, but also left, 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 to where our x value is -infinity. So we are increasing from -infinity to that extrema value right about there, which is an x value of -0.5. Now, we are increasing from -infinity all the way until that x value, and then once we hit it, the extrema value, we start to go down. We turn, so that is our turning point. So we are then decreasing from -0.5 all the way to the right and down. But remember, the furthest to the right we can go is +infinity. Now, our domain should be a combination of our increasing and decreasing intervals, because remember, those should be x values. So if you were to put those intervals together, we get our domain. But we can really look at this and say, okay, well, we know how quadratics work. They go all the way to the left and all the way to the right without anything stopping them. So our domain is all real numbers, -infinity to infinity, which is actually what we would get if we added these two together. Now our range. Domain is left and right, and range is up and down. We've got arrows pointing down, so we're going to keep going down. We're going to go all the way down towards a y value of -infinity. And we are going to go up, but then we stop because we've got that highest point. So that means that we're going to go all the way until our y value of 4.5. And because we actually hit at 4.5, I am going to put a bracket. Now, some of you might ask, why don't I use brackets down here? And the reason that is you can see these share an x value of 0.5. Who's to say whether that point is included in the increasing section or the decreasing? Now, we can't really do that, so it is included in neither. And we keep them open as well. All right, so we've really got two types of problems here. We have our typical ones that we are going to analyze where our function is in standard form. And we can get most of the behavior, most of the analysis portions, just like we used to do. We can find the end behavior from degree and leading coefficient. We can find the zeros from factoring, y-intercepts from plugging in 0. Domain and range we can get from the graph, but we can also get from our equation, knowing the degree and the leading coefficient. That usually gives us some important information. But the extrema values, our local and absolute maximums and minimums, are things that for now we are going to need to get from a graph. All right, so the graph is going to be our analysis tool here. All right, let's also talk about turning points. Turning points are the number of extrema values. So looking at a function from the very beginning, we can determine the number of turning points it could potentially have. So in this case, we look at this function, the degree is 3. 3 is odd. That means the number of turning points is going to be even numbers less than 3. So we could have 2 turning points, which we do, or we could have 1 and it would look something like that. Now, the example we use is if we had a degree of 7, then that means even numbers less than 7 are possible turning points, 6, 4, 2, or 0. Now, if we look at this one down here, we've got an even degree because there are 2 factors. That means the degree is 2. And so we need odd numbers less than 2. And in this case, it is just 1. So the only possible turning point for us is 1, which makes sense because this is a quadratic. All right, so this is all the time we have for today. There's a lot that goes into this, but if you realize most of this is stuff we've seen before. The only things we have not seen or discussed is the extrema values, local and absolute, and I guess turning points as well. But those local and absolute extrema values we get from graphs. So it's not really anything that you are expected to do on your own. You just really need to know what you're looking for. Okay? Thank you for joining. If you have any questions or concerns, please feel free to reach out. Thanks.